For nearly a century, there was a map of the universe, the Big Bang, gravity, galaxy formation. Everything was in a logical order. But we were wrong, terribly wrong. When the James Webb Space Telescope looked to the dawn of the universe, everything shattered. It found massive galaxies formed in an impossible time, just 300 million years after the Big Bang. But these were nearly equivalent to the mass our Milky Way took 10 billion years to achieve. What's more, they contained oxygen, meaning multiple generations of stars had already died. But that is not the most disturbing part. A Nobel Prize-winning physicist says, "Our entire model of cosmology could be broken. If the thought of shattering everything you know about the beginning of the universe excites you, then like this video and join the channel. Because what you're about to see will make you question 13.8 billion years of cosmic understanding from its very foundation." Let's begin. For the better part of a century, our picture of the universe's origins was built on a solid framework. We called it the lambda CDM model. This model described how the universe expanded after the Big Bang. It explained how matter clumped together under gravity. It showed how the first stars and galaxies formed. Because this model was one of the most successful predictive frameworks in the history of science, confirmed again and again by decades of observations from thousands of scientists and dozens of telescopes. But then James Webb looked into space, and the early universe showed it a completely different face. What Webb saw was nothing anyone was prepared for. So, we must go back to the very beginning. Not of the story, but of everything, or at least the beginning we thought we understood. The universe had an instruction manual. Its name was lambda CDM. Lambda was the term that best described the mysterious dark energy responsible for the universe's accelerating expansion, a term Albert Einstein first added, then called his greatest blunder, but which turned out to be real. CDM stood for cold dark matter. This was a type of invisible matter that doesn't interact with light, but it does interact with gravity. That's why it makes up roughly 85% of all matter in the universe. Dark energy and dark matter were the two great unknowns at the heart of our standard model. But even though we didn't fundamentally know what they were, the model built around them worked with extraordinary precision. Until Webb took the stage. The James Webb Space Telescope was not designed to break cosmology, because its primary purpose was to see further back in time, deeper into the past, than any instrument before it. To witness that epic era when the first stars and galaxies were born, to fill the observational gaps that stubbornly remained since the Hubble Space Telescope era. Webb can do this because it sees primarily in infrared light. This is the part of the electromagnetic spectrum that carries the ancient signals from the most distant objects in the universe. The reason for this is a phenomenon called redshift. As a galaxy moves away from us, the light it emits is stretched by the expansion of space. The faster it recedes, and the farther away it is, the more its light shifts toward red, and then beyond red, into the infrared. For objects that existed when the universe was only a few hundred million years old, this light has been stretched so dramatically that it is now entirely in the infrared range. Hubble could see a part of this, but only a small part. Webb, with its mirrors collecting area about 7 times larger than Hubble's, and its specially calibrated instruments, was built to see this light clearly. But what did scientists expect to find in that early epoch? A kind of rough draft. Dim, small, irregular proto-galaxies, the raw materials of a cosmos that had not yet had time to assemble itself into anything elegant. Theoretical models predicted that galaxy formation was a slow, gradual process. Matter had to collapse under gravity just to form stars. Those stars had to live and die, enriching the surrounding gas with heavier elements. Only then could new generations of stars form, and over hundreds of millions, then billions of years, this slow accumulation would produce the large, structured and bright galaxies we see in the nearby universe today. That was the expected timeline. That was what the lambda CDM model predicted. That was what everyone was prepared to see. But Webb saw something else. In the first deep field images released to the public in the summer of 2022, Webb revealed bright, structured and massive objects. These objects were found at distances and redshifts that placed them in the earliest epochs of the universe. Some appeared to exist when the universe was less than 500 million years old. A few even seemed to emerge when the universe was just 200 or 300 million years old. And these were not the dim, formless blobs the models had predicted. On the contrary, they were extremely bright. They contained enormous numbers of stars. Some even appeared to have already developed the kind of internal structures that, according to our best theories, should have taken billions of years to evolve. This was not just surprising, it was, by the standards of existing physics, nearly impossible. So what did scientists do? Did they panic? No. The initial reactions were properly cautious, because these first estimates were photometric redshift estimates, based on an object's color change across different wavelength bands, and they could be wrong. Or so, they decided to wait for spectroscopic confirmation, the more precise measurement. This confirmation was the kind of sensitive wavelength analysis that gives an object's precise redshift, and therefore its precise distance and age, and the expected spectroscopic confirmations came. But, instead of solving the problem, they deepened it, because they showed that these objects were really there, really that old, and really unbelievably massive. This situation began to shake one of the most fundamental pillars of theoretical cosmology. Because the problem wasn't just that these galaxies were surprising, the problem was that their existence, if taken at face value, required a rate of star formation that existing physics could not easily explain. What does this mean exactly? Well, after the Big Bang, the universe was filled with a hot, dense plasma of particles. As it expanded and cooled around 380,000 years later, this plasma cooled enough to form neutral hydrogen atoms. This was the moment of recombination, when the universe first became transparent to light. The light released at recombination is what we detect today as the cosmic microwave background. So, after recombination, the universe entered a period called the Cosmic Dark Ages. There were no stars yet, no galaxies, just a vast, nearly uniform fog of neutral hydrogen and helium. And in this fog, there were tiny density variations from place to place. These tiny density fluctuations, visible as slight temperature variations in the cosmic microwave background, were the seeds of everything that came later. Regions that were slightly denser on average attracted more matter under gravity. Over time, these overdense regions grew even denser, and eventually, they collapsed to form the first stars and the first galaxies. But this process takes significant time in the lambda CDM framework. The first stars are thought to have formed about 100 to 200 million years after the Big Bang. The first galaxies, built from these early star clusters, would have taken even longer, growing gradually through mergers and accretion of matter over hundreds of millions of years. Now consider what Webb found. It is finding galaxies within the first few hundred million years of the universe's existence, in some cases within the first 200 million years, that appear to have accumulated stellar masses equivalent to hundreds of billions of solar masses. And to put this in perspective, our own Milky Way galaxy has been assembling its stars for about 10 billion years, and it has a stellar mass of perhaps 200 to 400 billion solar masses. But Webb is finding objects that appear to have reached comparable masses in a tiny fraction of that time, in an early universe where, according to lambda CDM, the raw material should not have been dense enough, and the physical conditions should not have been conducive to such rapid star formation. The question this raises is not just observational, it is a deeply physical one. Where did all this mass come from? And how did it turn into stars so quickly? In a typical galaxy today, star formation efficiency is quite low. Only about 10% of the gas in a galaxy eventually forms stars, because the rest either remains as diffuse gas, is heated by stellar radiation, or is blown out by supernova explosions and powerful winds from massive stars. This 10% efficiency is not an accident. It is the result of well-understood physical processes. But the galaxies Webb found in the early universe seem to have converted their gas into stars with efficiencies far exceeding 10%. Some analyses even suggest efficiencies approaching or even exceeding 100%. This is, in the simplest sense, physically impossible, because you cannot create more stellar mass than the gas you had to begin with. When an analysis returns an efficiency of 100% or higher, it doesn't say something magical happened. It actually says that our models for how much gas was available in those regions at that time are inconsistent with the amount of stellar mass we observe. Something is wrong with our accounting, and we need to find out what. So, scientists are debating multiple possible scenarios that could explain this discrepancy. The first and perhaps most conservative explanation is that our observations are being distorted by gravitational lensing in ways we haven't fully accounted for. Gravitational lensing occurs when the mass of a foreground object bends the light from a more distant background object. This bending can make the background object appear brighter and larger than it actually is. If some of the massive early galaxies Webb has detected are being lensed by foreground structures we haven't identified, then their apparent brightness, and therefore their apparent stellar mass, could be exaggerated. Once corrected for lensing, they might become much less extreme. But there is a problem with this explanation being a complete answer. Lensing can increase an object's brightness, but it doesn't change its redshift. So, a galaxy still existed at that time. Lensing just means we might have overestimated its mass a bit. For the most extreme objects, even generous lensing corrections still leave them in an uncomfortable territory for our models. These mysterious discoveries have caused us to question everything we know about the beginning of the universe. The models we have trusted for years were proving inadequate against the data sent by Webb. So, it wasn't just that a few galaxies were bigger than expected, it was that the entire picture of the early universe needed to be redrawn. These new and unexpected findings brought the most fundamental questions of cosmology back to the forefront. How could these massive structures form so early and so quickly? Were the physical mechanisms that formed them different from what we know? And what was the real story behind these discoveries? Beyond the observations, what are these objects themselves telling us? And now comes the real shock. Because, beyond the theoretical debates, there are the concrete objects Webb has found. Mere objects that even on their own could force a rewrite of cosmology textbooks. It is time to stop talking about concepts and start talking about facts, introducing the galaxies that shouldn't exist and the mysterious objects that hold the deepest secrets of the universe. Get ready, because everything starts now. The first category consists of the most extraordinary early epoch objects Webb has found. They are simply called massive early galaxies. These galaxies are found in an era corresponding to the first billion years of the universe, roughly at redshifts between 6 and 10, and in this short time, they appear to have accumulated stellar masses comparable to or exceeding the Milky Way. There is not necessarily anything unusual about their appearance. They look like galaxies. They have stellar populations. They emit light in ways consistent with stars. But they are far too big for the era in which they formed. One of the most striking examples of this is an object known as JADES-GS-Zs, 14-0. This is one of the most distant, spectroscopically confirmed galaxies ever found. It existed when the universe was only about 290 million years old, but it already contained hundreds of millions of solar masses worth of stars. It was actively forming stars at a rate that, if sustained over the age of the universe at that point, would require a nearly perfect conversion of gas into stars. Not only that, it was also producing oxygen. Oxygen is a heavy element that can only be created in the cores of massive stars and distributed by supernova explosions. So, this meant that multiple generations of stars had already lived and died inside this galaxy, before the universe was even 300 million years old. This point deserves a moment's pause. Because when we detect oxygen in an early galaxy, we're not just detecting a chemical element, we're detecting the result of entire stellar life cycles, stars that burned their nuclear fuel for millions of years and exploded as supernovae, and each explosion seeded the surrounding gas with the heavy elements forged inside the star. The presence of oxygen in a galaxy that existed 290 million years after the Big Bang meant that these cycles of stellar birth and death had already begun, before the universe had even reached 3% of its current age. This seemed impossible, but it was there, but. The second category was the truly mysterious and controversial one. These were the objects known colloquially as little red dots. This name hides their innocence. Because they appear in Webb's infrared images as compact, point-like or nearly point-like sources with distinctly red colours. They are found across a wide range of redshifts corresponding to the first 1 to 2 billion years of the universe, and there are far more of them than anyone expected. As researchers began to catalogue them, they found hundreds in a single deep field image. This was far more than models had predicted would exist. What makes the little red dots so perplexing is that they are difficult to classify. In terms of their light output, they resemble quasars, which are the extremely bright cores of galaxies powered by supermassive black holes. But their appearance is more compact, and their light profiles at some wavelengths are more consistent with dense stellar populations than with the pure point-like emission expected from a quasar. Some show spectral features that suggest both stellar emission and emission from an active galactic nucleus, that is, from gas heated by a feeding supermassive black hole. They seem to be something in between, something that doesn't fit neatly into the categories our classification systems were built for. This situation baffled scientists. Because gas want, they had hundreds of objects of unknown nature, and each one challenged all known categories. And now, for the real shock. The most careful spectroscopic analyses of the little red dots revealed a particularly strange feature. They showed extremely broad emission lines in the light from hydrogen and other atoms. Broad emission lines in galaxy spectra are typically associated with gas moving at very high velocities near a supermassive black hole. Because the width of an emission line is related to the range of velocities of the gas that produces it, and very broad lines mean gas moving at thousands of kilometers per second. This is the signature of matter orbiting at close range around a black hole. This strongly suggests that many of the little red dots contain active supermassive black holes at their centers. But here's the problem. The black holes implied by the emission line widths and the overall brightness of many little red dots are very, very big. Some analyses suggest black hole masses of tens of millions to hundreds of millions of times the mass of the Sun, and these massive black holes appear to have existed when the universe was only 500 million to 1 billion years old. Under standard black hole growth models, it is extremely difficult to grow a supermassive black hole of that mass in that amount of time, because there is a physical limit to the rate at which a black hole can accrete matter. This limit is called the Eddington limit. Even if a black hole accreted matter continuously at the Eddington limit from the moment of the Big Bang, it would need to start from a seed of at least a certain minimum mass to reach 100 million solar masses within the first billion years. Starting from a stellar black hole of 10 or 20 solar masses does not give enough time. This was something physics told us. But Webb's findings suggested that physics might be wrong, and yet, this seed problem for supermassive black holes was not actually new. It was a known tension in cosmology even before Webb, because the existence of quasars at redshifts of 6 and 7, corresponding to the first billion years of the universe, already required explanations for how the black holes at their centers grew so quickly. The proposed solutions included heavy seeds. That is, black holes formed not from individual star deaths, but from the direct collapse of entire giant gas clouds. This scenario, bypassing the star phase entirely, produced black holes of perhaps 10,000 to 100,000 solar masses at the outset. Black holes with heavy seeds would have a significant head start in the race to become supermassive. But Webb's discovery of the little red dots did not make this problem easier. On the contrary, it made it much harder. Because the little red dots were far more numerous than the known early epoch quasars, and they spanned a wider range of cosmic epochs. If they all contained supermassive black holes, then massive black holes must have been extraordinarily common in the early universe, so common that no existing model of black hole seeding and growth could easily explain it. This situation pointed to the existence of a kind of black hole factory, a factory at the dawn of the universe, producing monsters of unbelievable number and size. The existence of this factory was demolishing our most basic cosmological assumptions. But some researchers suggested that not all little red dots might be powered by supermassive black holes, that perhaps some were instead powered by extremely compact, dense stellar populations, that is, galaxies that had somehow squeezed almost all of their stars into a very small volume, so small that their surface brightness was enormous, and their light profile mimicked a point source. If this is the case, then the broad emission lines required a different explanation. Perhaps they were caused by fast-moving gas driven by collective stellar feedback, rather than proximity to a black hole. Other researchers suggested that the little red dots might represent a brief phase in the life of early galaxies, a violent Mian, short-lived period where intense star formation and black hole growth occurred simultaneously. This made the objects both very bright and very compact at the same time. After this phase, they might settle into more normal galaxy configurations, and they could become the ordinary large galaxies we see in later cosmic epochs. This burst scenario would mean we were catching these objects at a rare and transient moment, which could explain why they look so unusual. But none of these proposals could be definitively proven. The little red dots remain one of the most actively studied and most uncertain aspects of the Webb data, and new papers on them appear in the scientific literature almost every week. All these discoveries bring us to a name at the center of this story, a figure who deserves careful attention, a Nobel laureate whose serious claims have given this story its urgency. The physicist in question is John Mather. In 2006, he shared the Nobel Prize in Physics for his work on the Cosmic Background Explorer satellite. This was the mission that made the first precise measurements of the cosmic microwave background and confirmed the Big Bang model with extraordinary precision. Mather is not an outlier or a dissenter. On the contrary, he is one of the architects of the very framework that Webb's results are now challenging. And not by coincidence, he is also the senior project scientist for the James Webb Space Telescope. What Mather has publicly stated in interviews and discussions with science journalists following Webb's initial results is his belief that Webb's first results may represent a genuine challenge to our understanding of early cosmic history, a challenge that might require revisions that go beyond small parameter adjustments. As a scientist should, he has been careful to frame his statements as serious questions rather than definitive conclusions. But, given his background and his central role in the mission, these are not casual comments. They represent a considered judgment that the observations are anomalous enough to demand that we rethink our theoretical framework. And that judgment is echoing throughout the entire cosmology community. Because, when Mather speaks, everyone listens. These massive galaxies, these mysterious little red dots, and these black holes of unimaginable size. They all tell the same story. The beginning of the universe was far more complex and far more active than we thought. But how exactly did these objects come to be? How do the physical processes that formed them deviate from the laws we know? And do these anomalies spell the end of the lambda CDM model? To answer these questions, we must now go beneath the surface, into the world of theories, models, and the most fundamental physical constants, because the answers lie in the mechanisms of the universe's most basic operations. So what is behind this? We've seen that Webb's findings are challenging the lambda CDM model, but what does it mean for a cosmological model to be wrong? And what could replace lambda CDM? Let's get technical. Because the answers to these questions lie in one of the most exciting fields of science. Lambda CDM is not wrong in the way a numerical calculation is wrong, because it is a theoretical framework with enormous predictive success across many different observations. It correctly predicts the observed abundances of light elements produced in the first few minutes after the Big Bang. It correctly predicts the pattern of temperature fluctuations in the cosmic microwave background. It correctly predicts the large-scale distribution of galaxies on scales of hundreds of millions to billions of light-years. So, these are not minor successes. They are remarkable triumphs of theoretical physics applied to the cosmos. Where lambda CDM is challenged is in the small-scale behavior of dark matter and, as it now seems, in the history of early galaxy formation. These failures are real, but they are not the kind of complete failure that requires throwing out the whole framework. They are more like the failures that historically lead to the extension or modification of a successful theory. Just as Newtonian gravity was not wrong, but had to be extended to general relativity to handle extreme conditions, or as classical thermodynamics was not wrong, but had to be extended to quantum statistical mechanics to handle atomic scales. The most likely path forward for cosmology is not a wholesale abandonment of lambda CDM, but its refinement, a modification that preserves its many successes while resolving its failures in the early universe. But the real question is, what form will this modification take? So, one of the most discussed possibilities involves a phenomenon called primordial black holes. Primordial black holes are hypothetical black holes that formed not from stellar deaths, but directly from density fluctuations in the early universe, during or shortly after the Big Bang. If the early universe had sufficiently large density fluctuations, these dense regions could have collapsed directly into black holes before any stars or galaxies formed. Depending on when they formed and how large these fluctuations were, primordial black holes could have a mass ranging from subatomic particles to stellar mass and much more. This is like monsters being born in the cradle of the universe, before the stars were born. If primordial black holes formed in large numbers in the early universe, they could have many effects relevant to what Webb is seeing. They could have served as the heavy seeds for supermassive black holes. They could thus bypass the problem of growing them from stellar mass seeds in too short a time. They could also have served as additional gravitational centers around which gas could accumulate and form stars faster than in normal dark matter halos. They could even contribute to the dark matter budget. This could potentially explain part of why dark matter behaves the way it does. So, the primordial black hole hypothesis has seen a resurgence of interest as a potential partial solution to the early structure problem. But this hypothesis is controversial, and the constraints on the number and mass distribution of primordial black holes from various observational tests are complex and sometimes contradictory. Another possibility involves changes to the theory of inflation. Inflation is a theoretical period of exponential expansion thought to have occurred in the first tiny fraction of a second after the Big Bang. Inflation is used to explain several otherwise puzzling features of the observed universe, including its large-scale uniformity, the geometry of space, and the origin of the small density fluctuations that seeded all subsequent structure. In the simplest inflationary models, these density fluctuations have a specific statistical character. They are nearly scale invariant. This means that fluctuations of all sizes contribute roughly equally to the overall power spectrum of density variations. This prediction has been beautifully confirmed by measurements of the cosmic microwave background, but nearly scale invariant still allows for small deviations, and these deviations have huge importance for what the early universe looked like. If inflation produced slightly more small-scale power than the simplest models predict, then the overdense regions that seeded the earliest galaxies would have been denser than standard models assume. This would cause them to collapse faster and produce denser structures earlier. This enhanced small-scale power could potentially explain why Webb is finding larger galaxies earlier than expected, and without requiring any changes to the fundamental physics of how galaxies form once the initial conditions are set. This kind of modification is attractive because it doesn't require inventing new physics for dark matter or revising our understanding of gravity. It just requires the mechanism of inflation to have been slightly different from the simplest version. But the challenge is that enhanced small-scale power is constrained by other observations, and keeping it consistent with the cosmic microwave background and large-scale structure measurements while fitting the Webb data requires careful modelling. And then there is another class of explanation, one that sits on the more speculative end of the scientific spectrum, but is being taken seriously by a group of researchers. This is the possibility that what we are seeing in the early universe is not a result of unusually fast galaxy formation, but rather a result of the universe being older than we think. Some physicists, including the intellectual descendants of the Nobel laureate Subrahmanyan Chandrasekhar, have long questioned whether the Big Bang model in its current formulation is the only consistent cosmological framework. Or one particular proposal, associated with the work of Rajendra Gupta at the University of Ottawa, and explored in the context of his tired light plus varying constants models, suggests that the redshift of distant galaxies may not be entirely due to the expansion of space. In the standard model, all cosmological redshift is expansion redshift. But in tired light models, photons lose energy as they travel through space, not because space is expanding, but due to an interaction with the intergalactic medium, or a property of the photons themselves, and this energy loss manifests as a redshift. Gupta's proposal is not a simple tired light model. It also suggests the possibility that the physical constants of nature, such as the speed of light, the gravitational force, and Planck's constant, may not be strictly constant, but may vary slowly with cosmic time. If correct, the implication of such models would be that the universe is significantly older than 13.8 billion years. Gupta's specific model suggests an age closer to 26.7 billion years. A universe twice as old as our current estimate would have had twice as much time to form galaxies and accumulate stellar mass. This would make the massive early objects Webb has found much less surprising. But it is important to be honest about the scientific status of these models. They are not mainstream. They face significant observational hurdles, and most cosmologists approach them with skepticism. But the fact that they are being published in peer-reviewed journals shows how seriously the Webb observations are being taken. Because these data may be pointing to something fundamentally missing in our standard model. So, even the most radical ideas are on the table. But, alongside these radical ideas, there are other, more conservative but still significant mechanisms. One of these relates to the initial mass function of stars. The initial mass function, or IMEF as astronomers call it, is a concept that describes the distribution of stellar masses when a population of stars forms. Just like the trees in a forest are all different sizes, in our local universe and in the galaxies we can study in detail. There is a characteristic distribution: many small, dim, long-lived stars, fewer medium-mass stars like our Sun, and relatively rare, very bright but short-lived massive stars. The overall brightness of a galaxy depends heavily on this distribution, because massive stars, though much rarer, are many times brighter than small stars. So, when we estimate the stellar mass of a distant galaxy from its brightness, we use an assumed initial mass function. But what if the early universe produced stars with a different initial mass function, one that was more weighted towards large, bright stars? In this scenario, the same brightness would correspond to a much smaller total stellar mass than our standard calculations suggest. A galaxy that appears to contain 500 billion solar masses of stars based on a standard initial mass function might in fact only contain 50 billion solar masses if its stars were predominantly high mass and therefore much brighter per unit mass. This idea is not new. Theorists have long thought that the very first generation of stars, called population 3 stars, might have been exceptionally massive, perhaps hundreds of times the mass of the Sun. Because just the gas from which they formed lacked heavy elements, which act as coolants and allow the gas to fragment into smaller pieces. So, this idea stands as an attractive proposal that resolves some of the tension. But it also brings its own complications, because massive stars live short lives and die as supernovae. These explosions release tremendous amounts of energy and heavy elements into the surrounding gas. A galaxy dominated by massive stars would be producing an extraordinary rate of supernova explosions, and all that energy could potentially stop star formation from continuing by heating and blowing out the gas, rather than sustaining it. So while this heavy initial function might explain some extreme brightnesses, it is not clear if it could sustain the long-term star formation rates needed to build up the masses Webb observes. And then there are the proposed changes to the nature of dark matter itself. The standard lambda CDM model treats dark matter as cold. That is, it moves slowly and clusters efficiently on small scales. This cold dark matter predicts a specific hierarchy of structure formation, where small dark matter halos form first, and then hierarchically merge into larger ones over time. But if dark matter were instead warm, meaning it has some residual thermal velocity that prevents it from clustering on very small scales, the hierarchy of structure formation changes. Warm dark matter models tend to produce fewer small galaxies than cold dark matter models. This actually helps resolve a different tension in cosmology, called the small-scale structure problem. But they also tend to form large structures more slowly. This could worsen the tension with Webb's observations, rather than resolve it. Other researchers have suggested that dark matter might have a component that interacts through another force, not just gravitationally, or that it might decay or have a more complex particle physics than we currently assume. Some have even proposed entirely different frameworks for gravity itself, modifications to general relativity that change how gravity behaves on large scales or at early times. All of these ideas are being taken seriously and worked on mathematically. Because the observations demand it. When science knocks on the door of the unknown, even the most audacious ideas deserve a hearing. But before we dive into this entire theoretical landscape, we need to talk about the specific objects Webb has found, because they are not all the same, and understanding their different properties helps us understand the different explanations they might require. These objects are like a zoo at the dawn of the universe. Each one carries its own story, its own mystery, and its own challenge. Now, it is time to meet some of the strangest inhabitants of this cosmic zoo. Because Webb's eyes did not just show us large galaxies or red dots. It showed us beings that fit into none of our existing classification schemes, creating entirely new categories. These are the things that keep theorists awake at night, forcing them to rerun simulations and question their most basic assumptions about the cosmos. Understanding what these entities are is not just an astronomy problem. It is a testament to how creative and unexpected the universe can be from the very beginning. And all the mechanisms we have seen so far, primordial black holes, changes in inflation, the initial mass function, and even the idea of doubling the age of the universe, all are trying to solve the same fundamental problem. The early universe formed structure much faster than our models allowed. But what is truly exciting is that these theoretical debates have concrete, observable consequences. This is not just a game of mathematics. Every single oversized galaxy, every mysterious red dot that Webb finds, is a piece of evidence that tests, confirms, or refutes one of these theories. And now, it's time to look at the most shocking, most direct, and most dramatic evidence of all. We will now stop talking about theoretical possibilities and focus on what the telescope actually saw. As because the section we are entering now is the climax, the place where data collides with theories and a new understanding is born. Now, we're going to the moment where everything changed, and now comes the miracle. The theoretical debates are over. The speculations have ended. Now there are only raw, unfiltered, spine-bending facts. Because when we look into Webb's deep fields, we're not just seeing a few anomalies, we're on the verge of a revolution. This is the climax of the video, the moment where everything comes together, where theories collapse, and a new universe is born. Now, with the most powerful telescope in human history, we embark on the deepest journey to the beginning of time. Fasten your seatbelts, because what you're about to see will push the limits of your imagination. The greatest secrets of the universe are now being revealed. The first shock, its name, JADES-GS-Z14-0. It should not have existed, but it was there. Webb saw it, and the world of cosmology was shaken to its core. This was not just a galaxy, it was an impossibility. Its light had been traveling to us for more than 13.5 billion years. This makes it one of the most distant galaxies ever spectroscopically confirmed. Its redshift value is precisely 14.32. This is a record number. This means this galaxy existed when the universe was only 290 million years old. Just 2% of its current age. 290 million years. Think about it. About the same amount of time that has passed since the first four-legged animals began to walk on land. But inside this cosmic infant, there were hundreds of millions of solar masses worth of stars. Not only that, Webb detected oxygen inside it. This is a heavy element, and it can only be created by the deadly explosions of massive stars, supernovae. So, inside this galaxy, before the universe was even 300 million years old, at least one, perhaps several generations of stars had to have been born, lived, and died. How is this possible? The standard lambda CDM model did not allow for the accumulation of such great mass and such chemical richness in such a short time. This was like a baby running a marathon a few minutes after being born. Scientists were in shock. Papers published in 2024 described how this single object was upending our current models of galaxy formation. JADES-GS-Z14-0 was a revolution in itself. But this was only the beginning. But there was something bigger, more mysterious. Little red dots. The name hides their innocence. Because they could be the heralds of the universe's most violent monsters, hundreds of them. They appear in every deep field Webb looks at, compact, red, and their numbers are hundreds of times greater than the most optimistic models predicted. This was a shock in itself, but the real bombshell was hidden in their spectra. These spectra showed gas rotating at unbelievable speeds, up to tens of thousands of kilometers per second. This can be the signature of only one thing: a feeding, supermassive black hole. And these black holes were not small. Analyses pointed to masses of tens of millions, even hundreds of millions of times the mass of the Sun. When the universe was only 500 million to 1 billion years old, this was beyond impossible. Because there is a physical limit to the growth of a black hole, the Eddington limit. Even at this limit, there was not enough time for a black hole of 10 or 20 solar masses, born from the death of a star, to reach these gigantic sizes. Billions of years were needed, not hundreds of millions. This discovery shattered black hole formation theories. Astronomers like Alison Kirkpatrick from the University of Kansas described these objects as unlike anything seen before. The scientific world had to confront the idea that the early universe might harbour a black hole factory. Hundreds, thousands, perhaps millions of giant monsters growing silently at the dawn of the cosmos, and then the most incredible thing happened. These two great mysteries merged, led to because. Researchers realized that these massive early galaxies and the little red dots might actually be different chapters of the same story. This was a scenario called early quenching. According to this scenario, the early universe was witnessing a violent co-evolution of black holes and galaxies. Both were growing at an incredible rate and regulating each other. First, a giant gas cloud collapses, but instead of forming stars, it directly forms a heavy seed black hole of 100,000 solar masses. This black hole begins to devour the gas around it voraciously. This makes it shine as a little red dot. But the immense energy released in this process, so-called AGN feedback, sweeps the remaining gas out of the galaxy. This suddenly stops or quenches star formation. The result? A red and dead galaxy that has reached a massive size in a short time, but is no longer forming new stars. A scenario that could explain some of the features of objects just like JADES-GS-Z14-0. This solved both great puzzles with a single, elegant, but terrifying mechanism. The early universe was filled with black hole factories as much as star factories, and these two forces were locked in a deadly dance that determined the fate of the cosmos's first structures. This idea radically changed modern cosmological simulations. Codes like illustrious TNG and Eagle are being rerun to test these new early feedback scenarios. Because Webb's data was saying that the beginning of the universe was much more violent, much faster, and much more black hole-centric than we thought. But the real earthquake occurred when the statistical significance of all these findings was understood. This was not a single strange galaxy or a few hundred red dots. This was a systematic anomaly. Deep field surveys like JADES and SEERS were consistently finding a greater number of massive early galaxies than lambda CDM predictions. The difference was not just a few. In some mass and redshift ranges, the difference was hundreds of times. Hundreds! This could not be a measurement error. This was the strongest evidence that the model was fundamentally wrong. Imagine you have a map. This map tells you there should be only one mountain in a certain region. But you go there and see a mountain range consisting of hundreds of mountains. You understand that your map is wrong. This is exactly what cosmologists felt. Their map, lambda CDM, was drawing the geography of the early universe completely wrong. This abundance problem became the biggest headache for theorists, because you couldn't solve it by slightly changing the parameters. This showed that the framework itself was broken. This situation led even the architects who built the model, like John Mather, to say, we may need to rethink our theoretical framework. The scientific community felt a decades-long consensus cracking. The reign of lambda CDM might be coming to an end, and this was both terrifying and incredibly exciting, because it meant the beginning of a new era of physics, and just when you thought things couldn't get more complicated, Webb delivered its final blow. This blow came not from the galaxies themselves, but from the space between them, the epoch of reionization. This is the period when the universe emerged from the Dark Ages and was reionized by the light of the first stars. According to the Standard Model, this process should have been completed about 1 billion years after the Big Bang. But Webb's data provided strong clues that this process might have been completed much earlier. How? By studying the spectra of distant quasars, the Lyman alpha forest in these spectra. The absorption lines created by neutral hydrogen is like a thermometer showing the ionization state of the universe. Webb saw much less neutral hydrogen absorption in the spectra of some very distant quasars than expected. This meant that those regions of the universe were fully ionized at a much earlier time than the models predicted. How is this possible? There is only one way: a much larger number and much brighter ionizing sources than the models accounted for. That is, a greater number and brighter early galaxies, just like what Webb found. This was the final link that connected all the pieces: massive galaxies, little red dots, giant black holes, and early ionization. They all said the same thing: the early universe was far more energetic, far more efficient, and far faster than theory allowed. This could be a fatal blow to lambda CDM, because this was no longer the story of just a few galaxies. This was the story of the entire universe, the entire cosmic web, the entire history. And this story was completely different from the one we had written. All these shocking discoveries, these epic findings, these shattered theories, they all converge on a single question. So what does it mean? These massive structures, these mysterious monsters, this unexpected speed. What do they tell us about the universe itself? We now know that something is deeply wrong. But what is the nature of this wrongness? Does it just require a small adjustment? Or do we need to rethink everything from the very beginning, starting with the Big Bang itself? Because this door that Webb has opened leads not just to new galaxies, but to a new physics, a new cosmology, and perhaps a completely new understanding of the universe. And now, it is time to step through that door. Because the real adventure is just beginning. Because the meaning of these anomalies is causing us to question everything from the age and fate of the universe to the most fundamental laws of physics. SEO scientists are now considering even the most radical possibilities, and each of these possibilities is more shocking than the last. This is not just a revision of a model, this is a paradigm shift, a moment that is redrawing the portrait of the cosmos. Now, we will look even more closely at the most shocking details of that portrait. And then, Webb's methodology itself created a revolution. This was not just about what it saw, but how it saw it. Introducing the Lyman break technique. This is one of the most powerful tools used to measure a galaxy's distance. The logic is simple. Hydrogen atoms completely absorb ultraviolet light above a certain energy. This energy level is called the Lyman limit. So, in a galaxy's spectrum, there is almost no light at wavelengths shorter than this limit. Like a cliff, a break, where for nearby galaxies, this break is in the far ultraviolet region, which telescopes cannot see. But, as the universe expands, this break also redshifts. At redshift 6, this break comes to about 9,120 angstroms, the beginning of the infrared. At redshift 10, it reaches 1.2 microns, and at the record-breaking redshift 14, it comes all the way to 1.7 microns. Webb's NIRCam instrument was designed to see this very region and from 0.6 to 5 microns. This was an area where Hubble was blind. When Webb sees that a galaxy is bright in multiple infrared filters, but suddenly disappears in a shorter wavelength filter, it has found a break galaxy. And the location of this break gives its redshift, its distance, with incredible precision. This method revolutionized photometric redshift estimates. Because it was no longer based just on colors, but on a physical break. This was like estimating the distance of a ship miles away by watching it suddenly disappear into the fog. Thanks to this technique, Webb was able to identify hundreds, even thousands of high redshift candidate galaxies with incredible speed. This statistical power went beyond singular anomalies to prove that an entire population was in conflict with the standard model. This was a game changer for the scientific world. We were no longer looking at individual trees, but at the map of an entire forest. And that map looked nothing like anything we knew. But Webb had a more powerful weapon in its arsenal. Its name, NIRSpec, the Near-Infrared Spectrograph. This device is a work of art. And at its heart lies a technology called the micro-shutter array. This is a grid of 250,000 small controllable shutters packed into an area the size of a postage stamp. Each of these shutters is the width of a human hair. and each one can be opened and closed independently. What does this mean? It means that NearSpec can take the spectra of about 100 different objects in the sky simultaneously, in a single observation. 100! To do this, Hubble had to observe each object one by one, for hours, even days. Webb could do it all at once. This was an increase in efficiency of hundreds of times. The JADES program used this revolutionary technology to obtain the spectra of hundreds of galaxies in a single pointing. This allowed the photometric estimates to be confirmed with precise spectroscopic redshifts. And when those confirmations came, the collective breath of the cosmology community was taken away. Because most of the candidates were exactly where they were predicted to be, incredibly distant, incredibly large, and incredibly early. NearSpec's massive spectroscopy capability completely destroyed the hope that maybe it's just a measurement error. The problem was real, the anomaly was real, and now there was nowhere left to hide. Scientists were watching the theories they had trusted for decades crumble one by one, with the data coming from these small, programmable shutters. And it was at this very point that the story becomes even more personal. The Nobel laureate John Mather, the senior project scientist for the Webb telescope, that is, one of the chief architects of this revolutionary machine, thus Mather was a figure who had dedicated his career to confirming the lambda CDM model. His measurements of the cosmic microwave background with the COBE satellite had provided the strongest evidence for the Big Bang theory to date. But now, the very telescope he created was sending back data that was fundamentally shaking the structure he had built, and Mather, with the honesty befitting a scientist, confronted this reality. In his public statements, he said that Webb's findings showed that galaxy formation happened faster than we thought. He openly expressed the possibility that something is wrong in the model. This was like a general admitting that there were cracks in the walls of the fortress he himself had built. This required enormous intellectual courage. Mather's words sent shockwaves through the scientific world. Because this was no longer the fantasy of an outlier theorist. This was one of the most respected names in the field confronting the results of his own work. His words sent a message to the entire cosmology community. It is no longer time to cling to old dogmas. It is time to follow the data and go wherever it leads. Mather's stance represented the scientific process in its purest form, an unwavering commitment to the truth, which came even before personal beliefs and past achievements. This was proof that the Webb revolution was not just a technological one, but also a philosophical one. All these revolutionary discoveries, these broken records, these shaken paradigms, they bring us to one massive question. What if the universe is much, much older than we think? This is the most radical, most earth-shattering idea put forward by a few brave scientists like Rajendra Gupta. According to this idea, the redshift of distant galaxies is not just caused by the expansion of the universe. Part of it may be due to photons losing energy through the tired light principle during their billion-year journeys. This model also suggests that physical constants change over time. If this is true, the age of the universe might not be 13.8 billion years, but 26.7 billion years, almost double. This changes everything, because in a 26.7 billion-year-old universe, there would be plenty of time for galaxies like JA-DES-GS-Z 14-0 to form. There would be plenty of time for those massive black holes to grow. Although this idea is still met with great skepticism by mainstream science, Webb's data is so compelling that it can no longer be ignored. This shows how deep the so-called cosmological crisis is. Our most basic assumption, the age of the universe itself, is now on the table. This is one of the most exciting moments in science, a moment where everything is questioned and everything is possible. These epic discoveries, these broken records, these shaken beliefs, they show us that the universe is far stranger, far more creative, and far more mysterious than we ever imagined. But now it is time to stop and think. What does this cosmic drama, these events billions of light years away, mean for us? What is the connection between these massive discoveries and our existence on this small, pale blue planet? Because this is not just the story of galaxies and black holes. This is also our story, the story of our origins. and the time has come to ask the deepest questions about our place in the universe. Because this new cosmos that Webb has shown us may change not only astronomy, but also philosophy forever. So, who are we in this new universe? All these discoveries, these events billions of light years away, what do they mean for us? Now, it is time to stop and think. Because this new cosmos that Webb has shown us is reshaping not only astronomy, but also our deepest questions about existence. This is not just the story of galaxies and black holes, this is also our story, the story of our origins. And the time has now come to confront the deepest philosophical questions about our place in the universe. Because within this cosmic drama lie truths about what it means to be human that are both sorrowful and incredibly hopeful. The first contrast is about scale. On one hand, there is the James Webb Telescope, studying light that has travelled for more than 13 billion years. This light has travelled about 123,000 trillion kilometres. This is a distance the human mind cannot comprehend. On the other hand, there is you, a mortal being, about 1.7 metres tall, watching the data from this telescope. How can such a small and fragile being comprehend such an unimaginable magnitude? This is one of the most fundamental paradoxes of existence. It contains a truth that is both tragic and beautiful. The tragic truth is this: we will never physically reach those distances. We will never touch the dust of those first galaxies. We will never feel the warmth of the stars of JADES-GS-Z14-0. Those first moments of the universe will forever remain an unreachable memory for us. We are like a grain of sand on the shore of an ocean. We will never be able to swim the entire ocean. This can create a deep sense of cosmic loneliness and limitation. We are just temporary and small spectators on this immense stage. But this is where the but moment comes in. This is also the beautiful truth, because, yes, we are physically small, but our mind possesses a power that transcends this smallness. We may not be able to go there, but we can understand it. We can decipher the information carried by that 13 billion-year-old light. From the presence of oxygen, we can deduce that multiple generations of stars have lived and died. From the redshift of a light, we can calculate the age of the universe at that moment. This is the greatest triumph of human intelligence. We are not just passive observers of this universe. We are the parts of it that have become conscious. You are part of this paradox. You are an heir to this intelligence. You can build a world with your mind that you cannot see with your eyes or touch with your hands. This is our species' greatest superpower, to understand. And this struggle to understand is where we find our deepest meaning. The second contrast is about time. On one hand, there is a universe that is 13.8 billion years old, perhaps 26.7 billion years old, an ocean of time that seems infinite. On the other hand, there is an average human lifespan of 80 years, a moment shorter than the blink of an eye on this vast timeline. How can such a fleeting existence have any meaning in the face of such overwhelming eternity? This is another deep paradox at the center of the human condition. This also contains a truth that is both sad and beautiful. The sad truth is this: we are witnessing only a tiny moment of the cosmic story. We did not see the birth of the universe, and we will most likely not see its end. Billions of years passed before us, and billions of years will pass after us. Our existence is nothing more than a momentary foam in this vast river of time. This can create a sense of nothingness and transience. The thought that everything we do, every word we say, will be lost in this infinity can drive one to despair. But here comes that magical but moment again. This is also the beautiful truth, because yes, our existence is short, but this short moment is the moment the universe becomes aware of itself. For those 13.8 billion years, the universe was largely unconscious until we came along. Oxygen atoms were forged inside stars, carbon atoms formed planets and life, and finally, those atoms came together to form you, me, us, beings that think, feel, and wonder. We are the questions the universe asks itself. We are the way the universe marvels at its own beauty. Our short existence is what gives meaning to that infinite ocean of time. Because, thanks to us, the universe is no longer just existing, it is also known. You are part of this moment. Science-ski, your short life is one of the most precious moments in the 13.8 billion year history of the universe. A moment when the universe looks at itself. This gives you an incredible responsibility, and at the same time, an incredible privilege, to live this moment, to understand this moment, and to pass this moment on to those who come after you. The third contrast is between knowledge and mystery. On one hand, there is the incredible wealth of data provided by the James Webb Telescope, the spectra of thousands of galaxies, hundreds of articles, precise numbers that test, confirm, or refute our models, the golden age of knowledge. On the other hand, there are the 10 new questions that come with every new answer, the fact that every solved mystery reveals a deeper one. When we understand what the little red dots are, the question, so how are there so many of them, arises. When we explain how large galaxies formed, the question, so where did these rapidly growing black holes come from, appears. How can knowing more lead us to realize we know even less? This is the most fascinating paradox in the nature of science. The tragic truth may be this: perhaps we will never know everything. Perhaps the universe has a complexity that exceeds our capacity to understand. Perhaps we are like an ant trying to read all the books in a library. This can create a sense of inadequacy, the thought that our efforts are futile. But the beautiful truth is hidden here too, because the beauty of science is not in the destination, but in the journey itself. It is in that never-ending sense of wonder. It is in the excitement of not knowing what is around the next corner. Science is not a collection of knowledge. Science is a process of discovery, and this process will continue as long as there is mystery. This offers us an infinite playground, an infinite source of curiosity. You are part of this journey of discovery. Every why question you ask is a contribution to this great adventure. Your curiosity fuels the fire that drives humanity forward. Not knowing is not a weakness. Not knowing is an invitation to our greatest adventure. And the Webb telescope has sent us the most exciting invitation yet. These contrasts, the immense and the small, the infinite and the fleeting, knowledge and mystery, they offer us a deep perspective on our place in the universe. But perhaps the most important contrast is between loneliness and connection. Because, are we alone in this vast cosmos, or is everything connected by invisible threads? Because, the answer to this question may hold the most philosophical lesson Webb has shown us, and that lesson is actually proof of how deeply everything is connected, because the death of stars in those distant galaxies was a prerequisite for our existence. This is the greatest and most poignant poetry of the universe, the simultaneous existence of loneliness and connection. On one hand, there is the fact that each galaxy is a self-sufficient island, with millions of light-years of space between them. It takes millions, even billions of years for light to cross these distances. On the other hand, there is the fact that the carbon, oxygen, and iron atoms scattered into space by a supernova, exploding inside one of those galaxies, are the very atoms that billions of years later, here on Earth, make up the hemoglobin molecules circulating in your blood, the oxygen you breathe, or the neurons in your brain. How can a universe that seems so disconnected be so fundamentally interconnected? This is the very fabric of existence. The tragic truth is that we cannot directly feel this connection. We did not witness the moment of that star's explosion. We could not follow the billion-year journey of those atoms. We have only joined the final act of the story. This can create a sense of rootlessness. But the beautiful truth is that we carry the proof of this connection in our own bodies. We are stardust. This is not just a poetic phrase. This is a scientific fact. Every heavy atom in our body was forged in the heart of a star that died long before us. This establishes an unbreakable, physical bond between us and the universe. You are the living proof of this connection. The blood flowing in your veins is the legacy of a cosmic catastrophe from billions of years ago. Everything you look at, every word you speak, every thought you think, is a result of this long and complex chain. So, when you look at the night sky, you're not just seeing distant points of light. You're actually looking at your own family tree, your own cosmic ancestors, and this reminds us that even in the deepest moment of loneliness, we are never truly alone. But there is another, more subtle contrast, the dance between chaos and order. On one hand, there is the violence and chaos of the early universe that Webb shows us. Supernova explosions, voraciously feeding black holes, galaxies colliding with each other, a place where everything is in constant flux and change, where destruction and creation go hand in hand. On the other hand, there is the incredible order and complexity that arises from this chaos. The periodic table formed from the elements scattered by those explosions. The laws of physics that operate unfailingly even in the midst of that chaos. And ultimately, life itself, which emerged as a result of these processes. How can such a destructive and seemingly random process produce such orderly and predictable results? This is the greatest mystery of the universe's ability to self-organize. The tragic truth is that we often forget how fragile this order is. Our existence is the result of a series of cosmic coincidences and delicate balances that have lasted for billions of years. A small deviation in Earth's orbit, a small change in the sun's brightness, could end everything. We are like tightrope walkers. Below us is the bottomless abyss of chaos. But the beautiful truth is that this chaos is also the source of creativity. Without those supernova explosions, there would be no heavy elements. Without those galaxy collisions, new star formations would not be triggered. Chaos is the universe's way of renewing itself and creating more complex forms. Order arises from chaos and eventually returns to chaos. But this cycle is the engine of the universe. You are part of this dance. Your life is also a mixture of order and chaos. Plans get disrupted, unexpected things happen, but at the same time, these unexpected moments also offer the greatest opportunities for growth and creativity. When you understand this fundamental rhythm of the universe, you begin to see the chaos in your life not as a threat but as a potential, because the most beautiful melodies sometimes come from the most unexpected notes. And after talking about this entire cosmic journey, these immense scales and times, it all comes down to this simple, personal question: what do you feel? After learning this information, do you feel an overwhelming smallness or a deep connection with the universe? Both are correct and both are valid, because this is part of being human. To feel as small as a grain of sand, and yet to be able to carry universes in our minds. To know that we exist for just a fleeting moment, and yet to feel that moment gives meaning to eternity. To realize we are surrounded by the deepest mysteries, and yet to never give up the search for understanding. This duality is our greatest strength, because it keeps us humble, but at the same time, it gives us the courage to dream and to explore. This channel exists to be a safe space for your mind, a place where curiosity and calm come together, a space where the vastness of the universe transforms from overwhelming to soothing. If this sounds like something you need, please consider subscribing, because better sleep and deeper curiosity are always worth coming back for. Smallness and greatness, transience and eternity, knowledge and mystery, loneliness and connection, chaos and order. All these philosophical reflections show that the data Webb presents us with carries not only a scientific meaning, but also a deeply human one. We now know that our place in the universe is not a question with a simple answer. It is a dialogue that we constantly engage in, reshaping with every new discovery. But now, it is time to add a new layer to this dialogue. Because all these discoveries and philosophical thoughts bring us to a deeper question. Perhaps the most important question: is there an ultimate reason why the universe is so strange, so unexpected, and so complex? Or is everything just the result of blind chance and statistical probabilities? This is a question that pushes the boundaries of science, bringing us closer to the realms of theology and metaphysics, and now we will pursue this final and deepest mystery. Because this new universe that Webb has shown us is causing us to question not only how we exist, but also why we exist. And this questioning itself actually brings us to another, deeper question. Because all these questions, our search for meaning, are actually based on this fundamental truth: we are conscious beings. So, it is now time to face a more internal question. What do we do with this knowledge? How should knowing that the universe is so strange, so unexpected, affect our daily lives, our decisions, our values? This is no longer just about what we know. This is about how we live. Even because This cosmic portrait that Webb sends us illuminates not only astronomy books, but also the depths of our souls. First, we confront that delicate balance between certainty and uncertainty. On one hand, there is the incredible certainty that science offers us. Webb's NIRSpec instrument can measure a galaxy's redshift with incredible precision, like 14.32. The cosmic microwave background determines the age of the universe as 13.8 billion years, with a margin of error of only 1%. The laws of physics explain everything from the behavior of subatomic particles to the movement of galaxy clusters with astonishing accuracy. On the other hand, there is the deep uncertainty that every new discovery brings. The shaking of Lambda CDM's decades-long reign. The fact that even the age of the universe is beginning to be questioned. The fact that we have no definitive answer as to what the little red dots are. How can we know so much so certainly, yet at the same time be in such deep uncertainty about the most fundamental issues? The tragic truth is this: our search for certainty is part of our nature. We fear uncertainty. We worry about losing control, about not being on solid ground. So, when our models are shaken, we may experience a sense of loss and confusion. The thought that something we have believed in for years might be wrong is unsettling. But the beautiful truth lies here too, because progress in science comes precisely from the ability to embrace this uncertainty. If we thought we knew everything, we would never learn anything new. Uncertainty is the seed of curiosity and discovery. This is what scientists like John Mather do, aim to face the fact that even the models they have built might be wrong, and to be able to say, "I don't know, but I am here to learn." You constantly face this balance in your own life. You try to plan your career, your relationships, your future. You have a desire for certainty and control, but life constantly throws unexpected things at you. Uncertainties. What Webb teaches us is that we should not fear this uncertainty, to see it not as a threat, but as an opportunity for learning and growth. Because even our most solid beliefs can change in the face of new evidence, and this is not a weakness, but our greatest strength. Second, there is that strange relationship between individuality and universality. On one hand, there is your unique, singular experience, your memories, your dreams, your fears. In this universe, there is no one else with your fingerprint, your consciousness. You are an unrepeatable event among 8 billion people, and in 13.8 billion years of history. On the other hand, there is the fact that every single atom that makes you up is subject to the same fundamental laws as a star in the most distant corner of the universe. The gravity that holds you together also holds galaxies together. The chemical reactions in your cells obey the same laws of physics as the processes in distant nebulae. How can we be both such a unique individual and such an ordinary part of a universal process? The tragic truth is our potential to feel insignificant and lost in this universality. If we are all made of the same atoms and subject to the same laws, then what is the meaning of our individual lives? This can lead to existential anxiety. But the beautiful truth is that this universality is actually the strongest bond that connects us to each other and to the cosmos. Being unique does not mean we are alone. On the contrary, it means we are different members of a universal family. When you look at another person, you're not just seeing a different face, you're seeing a different configuration of the same stardust that makes you up. When you look at a tree, an animal, a star, you're looking at your own cosmic relatives. You stand right in the middle of this paradox. You're both a unique snowflake, and you're made of the same water. When you understand this truth, your capacity for empathy expands infinitely. Because the pain of others becomes your pain, the joy of others becomes your joy. Because, at the most fundamental level, we are all the same. We're all ways for the universe to experience itself, and this does not destroy our individuality. On the contrary, it gives it a deeper and more universal meaning. Third, we encounter that deep paradox between silence and message. On one hand, there is the overwhelming silence of the universe, a space that has been expanding for 13.8 billion years, largely empty and cold, a mechanism that operates according to blind laws of physics, showing no sign of purpose or intention. This is what is called cosmic silence, a frightening thought for many, the feeling that the universe is indifferent to us, that our existence means nothing to it. On the other hand, there is the fact that within that ancient light collected by the Webb telescope, there is an incredibly rich and complex message. That light tells us how stars are born and die, how elements are formed, how galaxies merge, how black holes grow. This is the universe's own autobiography, and we are the first beings able to read this autobiography. How can a universe that seems so silent also tell such a meaningful story? The tragic truth is that this story was not written for us. The universe is not trying to send us a message, it is just existing. And we, by chance, have evolved an intelligence that can read some of the traces of this existence. This, again, can lead to a sense of insignificance. But the beautiful truth is this: even if the story was not written for us, we can create the meaning. The silence becomes a message through the way we interpret it. Just as a painter looks at a blank canvas and sees a masterpiece, we too look at this raw data from the universe and create science, art, philosophy, and meaning. Meaning is not something found in the universe. Meaning is something we bring to the universe. You do this in every moment of your life. You impose a narrative, a purpose, a meaning on your life that seems like a series of random events. You are a creator of meaning, and this is perhaps our most godlike ability, the ability to turn the silence of the universe into a song. What Webb provides us are richer notes to compose this song, harmonies we have never heard before, certainty and uncertainty, individuality and universality, silence and message. These deeper philosophical layers show that Webb's discoveries are not just a scientific revolution, but also a revolution of consciousness. They give us the opportunity to rethink our place in the universe and how we should live with this knowledge. But this journey of thought is not over yet, because, beyond all these contrasts, there is one final insight, one final confrontation awaiting us. This is the most difficult, but perhaps the most liberating one yet. It is the ultimate conflict between our expectations and reality, and the outcome of this conflict could change our view of the universe forever. Because now is the time to break free from the final limitations created by our own minds, and to see the universe as it is in all its strange, unexpected, and mind-boggling glory. And this questioning itself brings us to a final contrast, perhaps the most important one: expectation and reality. On one hand, there is the human mind's inherent tendency to seek patterns, create stories, and fit the universe into an understandable, orderly framework. The Lambda CDM model was one of the most magnificent products of this tendency, an elegant, mathematically consistent, and satisfying story that explained observations for decades. On the other hand, there is the raw, complex, and often unaccommodating reality that the Webb telescope shows us. Little red dots, galaxies larger than they should be, a universe that models did not predict. How can the stories we so cleverly built be so ruthlessly demolished by the universe itself? The tragic truth is this: the universe has no obligation to conform to our stories. It is completely independent of our expectations, our desire for order, our search for meaning. This can create deep disappointment. The fact that a theory, a belief we have dedicated years to, can be shaken by a single observation shows how fragile our efforts are. But the beautiful truth lies in this very fragility. Because, when we let go of our expectations, we begin to see the universe as it is, in all its strange, unexpected, and mind-boggling glory. When we set aside our stories and allow the universe to tell its own, we encounter a much richer, much more interesting, and much more honest reality. Science is as much about realizing we've been asking the wrong questions as it is about finding definitive answers, and Webb is teaching us that we need to ask new questions. You experience this conflict between expectations and reality in your own life. You write a story about how your life should be, but reality often doesn't fit this story. In these moments, instead of being disappointed, you can remember the lesson Webb has taught us. Let go of your expectations and embrace reality as it is. Because the greatest growth, the deepest wisdom, comes when the stories we write collapse and we surrender to the universe's own narrative. This brings us to that final philosophical distinction between action and observation. On one hand, there is the immense, passive observation that Webb offers us. We collect light that has been travelling for billions of years. We analyse it. We try to understand it. But we cannot intervene in those processes in any way. We cannot change the fate of JADES-GS-Z14-0. We cannot feed or stop the black holes inside those little red dots. We are beings who cannot change the events on the cosmic stage, only watch. On the other hand, there is the deep internal change and potential for action that this observation creates in us. Knowing that the universe is so vast, so old, and so interconnected can profoundly affect our actions here on Earth, our responsibilities to each other and to our planet. How can such a passive observation give rise to such an active moral and ethical responsibility? The tragic truth is the difficulty of making this connection. In the rush of daily life, it is easy to forget what a galaxy billions of light years away has to do with our current decisions. This can create a sense of disconnection and indifference. But the beautiful truth is that this connection is the most fundamental reality of our existence. The laws of physics in those distant galaxies are the same laws that govern the climate, ecosystems, and life on our planet. When we understand how fragile and precious the universe is, we understand how fragile and precious our own little world is. We, as the parts of the universe that have become conscious, are tasked not only with observing, but also with protecting our own little blue dot. You are part of this responsibility. Everything new you learn about the universe is not just an intellectual exercise. It is also an opportunity to become a wiser, more compassionate, and more responsible person. Because to understand the universe is ultimately to understand ourselves, Ugysian, and when we understand ourselves, we can take the action needed to create a better world. At the end of this long journey, how do we feel? On one hand, there is the deep humility we feel in the face of the universe's unimaginable size and strangeness. On the other hand, there is the quiet pride that comes from having a mind that can comprehend this universe. Perhaps the right answer is somewhere in between. Perhaps wisdom is the ability to carry both of these feelings in our hearts at the same time. The life of John Mather perfectly summarizes this balance. On one hand, he makes revolutionary measurements that reveal the greatest secrets of the universe. On the other hand, he remains humble enough to accept that even the model he helped build could be wrong. Perhaps this is the most important lesson left to us at the end of this journey, to never lose our curiosity. But at the same time, to always leave a margin of doubt about what we know. Because the greatest discoveries often come from the most unexpected places, at the moment we are most certain. This is the greatest beauty of science and of life itself: expectations and reality, action and observation, pride and humility. These final philosophical thoughts show how rich the landscape is that we see through the window Webb has opened for us. We now know that our place in the universe is not a fixed point. It is a constantly expanding horizon of understanding. We know that even our most solid theories can be shaken by a single observation, and this is not a disaster, but an opportunity. We know that the silence of the universe can be turned into a song by our capacity to create meaning. And we know that the deepest connection in this vast cosmos is the very stardust that makes us up. This long and deep journey has touched the farthest corners of our minds in the most ancient moments of the universe. We're no longer the person we were at the beginning. Because when we learn something new about the universe, we actually learn something new about ourselves. And now, with all this knowledge and all these feelings, it is time to bring this great story to a conclusion. Because, at the end of every great journey, one must return home and put together what has been learned. And now, we have arrived at the final stop of this cosmic journey, the moment where findings, thoughts, and feelings converge. We have seen the mysteries in the first billion years of the universe. But I have not told you that the real chaos happened long before all these galaxies and stars. The fate of everything was determined in just 180 seconds. All the fundamental components of the universe were forged in the fire of those first 3 minutes. In our next journey, we go to those first 3 minutes, to the moment when time itself began, to the moment when the recipe for everything was written. Are you ready for order? our search for meaning. This can create deep disappointment. The fact that a theory, a belief we have dedicated years to, can be shaken by a single observation shows how fragile our efforts are. But the beautiful truth lies in this very fragility. Because, when we let go of our expectations, we begin to see the universe as it is, in all its strange, unexpected, and mind-boggling glory. When we set aside our stories and allow the universe to tell its own, we encounter a much richer, much more interesting, and much more honest reality. Science is as much about realizing we've been asking the wrong questions as it is about finding definitive answers, and Webb is teaching us that we need to ask new questions. You experience this conflict between expectations and reality in your own life. You write a story about how your life should be, but reality often doesn't fit this story. In these moments, instead of being disappointed, you can remember the lesson Webb has taught us. Let go of your expectations and embrace reality as it is. Because the greatest growth, the deepest wisdom, comes when the stories we write collapse and we surrender to the universe's own narrative. This brings us to that final philosophical distinction between action and observation. On one hand, there is the immense, passive observation that Webb offers us. We collect light that has been travelling for billions of years. We analyse it. We try to understand it. But we cannot intervene in those processes in any way. We cannot change the fate of JADES-GS-Z14-0. We cannot feed or stop the black holes inside those little red dots. We are beings who cannot change the events on the cosmic stage, only watch. On the other hand, there is the deep internal change and potential for action that this observation creates in us. Knowing that the universe is so vast, so old, and so interconnected can profoundly affect our actions here on Earth, our responsibilities to each other and to our planet. How can such a passive observation give rise to such an active moral and ethical responsibility? The tragic truth is the difficulty of making this connection. In the rush of daily life, it is easy to forget what a galaxy billions of light years away has to do with our current decisions. This can create a sense of disconnection and indifference. But the beautiful truth is that this connection is the most fundamental reality of our existence. The laws of physics in those distant galaxies are the same laws that govern the climate, ecosystems, and life on our planet. When we understand how fragile and precious the universe is, we understand how fragile and precious our own little world is. We, as the parts of the universe that have become conscious, are tasked not only with observing, but also with protecting our own little blue dot. You are part of this responsibility. Everything new you learn about the universe is not just an intellectual exercise. It is also an opportunity to become a wiser, more compassionate, and more responsible person. Because to understand the universe is ultimately to understand ourselves, accretion, and when we understand ourselves, we can take the action needed to create a better world. At the end of this long journey, how do we feel? On one hand, there is the deep humility we feel in the face of the universe's unimaginable size and strangeness. On the other hand, there is the quiet pride that comes from having a mind that can comprehend this universe. Perhaps the right answer is somewhere in between. Perhaps wisdom is the ability to carry both of these feelings in our hearts at the same time. The life of John Mather perfectly summarizes this balance. On one hand, he makes revolutionary measurements that reveal the greatest secrets of the universe. On the other hand, he remains humble enough to accept that even the model he helped build could be wrong. Perhaps this is the most important lesson left to us at the end of this journey, to never lose our curiosity. But at the same time, to always leave a margin of doubt about what we know. Because the greatest discoveries often come from the most unexpected places. At the moment we are most certain. This is the greatest beauty of science and of life itself. Expectations and reality, action and observation, pride and humility. These final philosophical thoughts show how rich the landscape is that we see through the window Webb has opened for us. We now know that our place in the universe is not a fixed point. It is a constantly expanding horizon of understanding. We know that even our most solid theories can be shaken by a single observation, and this is not a disaster, but an opportunity. We know that the silence of the universe can be turned into a song by our capacity to create meaning. And we know that the deepest connection in this vast cosmos is the very stardust that makes us up. This long and deep journey has touched the farthest corners of our minds in the most ancient moments of the universe. We're no longer the person we were at the beginning. Because, when we learn something new about the universe, we actually learn something new about ourselves. And now, with all this knowledge and all these feelings, it is time to bring this great story to a conclusion. Because, at the end of every great journey, one must return home and put together what has been learned. And now, we have arrived at the final stop of this cosmic journey, the moment where findings, thoughts, and feelings converge. We have seen the mysteries in the first billion years of the universe. But I have not told you that the real chaos happened long before all these galaxies and stars. The fate of everything was determined in just 180 seconds. All the fundamental components of the universe were forged in the fire of those first 3 minutes. In our next journey, we go to those first 3 minutes, to the moment when time itself began, to the moment when the recipe for everything was written. Are you ready?